Welcome to the NFPA 2400 electronic training program. This program is produced by Blue Ridge Mountain Drones in conjunction with Hunter Remote Aviation LLC. Please note that this program contains copyrighted materials from the National Fire Protection Association, the National Institute of Standards and Technology, Blue Ridge Mountain Drones, and Hunter Remote Aviation. Your mission as a professional remote pilot in command is to fly with a purpose and to have a sufficient plan to report reliable and actionable information to incident command. The basic concept of this class is to train and test proficiencies as a remote pilot in command and with the control systems of small unmanned aircraft systems. The primary foundation of this training is based upon NFPA 2400, standards designed for small unmanned aircraft systems, or SUAS, used for public safety operations. All first responder SUAS pilots should familiarize themselves with this standard, even non-firefighter pilots. Future NFPA 2400 certification classes may soon be available to you. There will not be a test at the end of this online training. However, your agency can utilize these standards and methods to test and certify the proficiencies of their pilots. If so, Blue Ridge Mountain Drones can offer further assistance. Scope. This standard shall cover the minimum requirements relating to the operation, deployment, and implementation of small unmanned aircraft systems, SUAS, for public safety operations. This standard shall establish operational protocols for public safety entities who use and support SUAS. This standard shall include minimum job performance requirements, known as JPRs, for public safety personnel who operate and support SUAS. This standard shall include minimum requirements for the maintenance of SUAS when used by public safety entities. This standard shall provide additional minimum requirements specific to public safety entities. Purpose. This standard shall specify the minimum criteria necessary to support safe, effective, and efficient SUAS operations when utilized by public safety entities. Application. The standard shall apply to all public safety entities operating SUAS. The standard shall apply to non-public entities who conduct SUAS operations for public safety. This standard shall apply to SUAS that weigh less than 55 pounds. Equivalency. Nothing in the standard is intended to prevent the use of systems, methods, devices, or technology of equivalent or superior quality, effectiveness, and performance over those prescribed by this standard. Technical documentation shall be submitted to the authority having jurisdiction to demonstrate equivalency. The system, method, device, or aircraft shall be approved for the intended purpose by the authority having jurisdiction. Enforcement. This standard shall be administered and enforced by the authority having jurisdiction. Application. Additional administrative information. This standard shall be divided based on the different types of minimum requirements for SUAS when used for operations supporting public safety entities. Chapter 4, shall include minimum requirements related to the organization, deployment, and selection of SUAS when used for operations supporting public safety entities. Chapter 5 shall include the minimum JPRs for remote piloting command and the visual observer for a UAS when used by public safety personnel. Chapter 6 shall include minimum requirements for maintenance of SUAS when used for public safety operations. Chapters 4, 5, and 6 shall contain the following administrative sections in relation to the applicable type of requirement. Number 1, chapter scope. Number 2, chapter's purpose. Number 3, chapter's application. And number 4, chapter's definitions. Definitions found in chapters 4, 5, and 6 shall be represented in chapter 3 in accordance with the Manual of Style for NFPA Technical Committee documents. Annexes shall provide explanatory information based on the applicable section number. Annex B shall contain an explanation of professional qualification standards and concepts of JPRs. The video you are about to see is an excellent representation of how a well-equipped SUAS can assist the incident commander with the application of water on a fire. The RGB image on the left side alone is not sufficient because of the reduced visibility caused by the smoke. The thermal image on the right shows the actual hotspots in the structure where the attack can be directed. This is a good example of efficient use of available resources. We're going to focus on, as a part of NFPA 2400, the requisite knowledge and requisite skills required to be a first responder SUAS pilot. These are known as pilotage skills. In addition to NFPA standards, the National Institute of Standards and Technology, also known as NIST, offers models for pilot flight training and testing methodologies for SUAS aircraft. These are documented in the NIST guidelines on robotic equipment. They have been adopted and refined for this training class. In this program, we're going to cover only 2 chapters of NFPA 2400, partially covering Chapter 4, the Organizational Deployment and Considerations for SUAS, and Chapter 5, Professional Qualifications for SUAS Public Safety Personnel. NFPA 2400 details the minimum requirements for the safe operation, deployment, and implementation of SUAS. This includes organization program criteria and considerations, professional qualifications for safety personnel, and elements of a maintenance program. Chapter 4, Organizational Deployment and Consideration for SUAS. The piloted skills of first responders, RPICs, are defined as job performance requirements, or JPRs. The deployment of SUAS operations shall be considered an additional segment of an operation or an operation of its own. The deployment of SUAS operations shall be assessed based on the following: mission objectives, risk assessment, the availability and capability of all resources. The Incident Command System is a standardized on-scene emergency management construct. The ICS is the combination of the following: facilities, equipment, personnel, procedures, and finally, communications. The ICS, operated within a common organizational structure, is designed to aid the management of all resources during an incident. SUAS team resources include clearly defined command structure with various roles and duties determined, trained and qualified personnel supporting the various roles within the incident command structure, facilities to house staff and equipment during downtime, capable aircraft and supporting equipment tested to ensure they meet mission requirements, transportation to deliver resources to emergency incident locations, a mobile command center and equipment to support incident command requirements, standard operating procedures and guidelines, including, most importantly, communication procedures. UAS team responsibilities: personnel trained and qualified, overall crew readiness, equipment maintenance and repair, operational procedures and communications, risk assessments, data acquisition, data dissemination and control, digital media as evidence, DME procedures. Data acquisition is the collection of information from SUAS for the purpose of fulfilling the mission objectives and goals in accordance with the mission plan. Therefore, the primary mission of a first responder UAS team is to collect and report reliable, actionable information, initially to incident command and possibly later to other interested parties. In the case of law enforcement, data collected may be used as evidence in court proceedings. Follow your agency's digital media as evidence DME policies. Basically, DME is the digital recordings of images, sounds, and associated data with probated values stored or transmitted in a binary form. All dissemination must be done in accordance with the agency policies and procedures. Traceability by documented hands-off is likely or necessary. HIPAA laws have been designed and implemented to protect the rights of patients. Ensure your staff has been adequately trained on these regulations. The diagram shown is an example of an incident command construct. Each agency will determine an organizational construct that suits their specific requirements. A public safety entity is any entity involved with public safety that has a mission to protect life, property, or the environment, or any combination of these elements. Public safety personnel are individuals involved with public safety that have a mission to protect life, property, or the environment, or any combination of these elements. According to NFPA 2400, there are 3 leadership roles within the construct of a public safety UAS team. Number 1, the incident commander, or IC. Number 2, UAS coordinator, or UC. Number 3, remote piloting command, or RPIC. The incident commander is the individual responsible for all incident activities, including the development of strategies and tactics and the ordering and release of resources. The IC has overall authority and responsibility for conducting incident operations and the responsibility for the management of all incident operations at the incident site. UAS coordinator. The UAS coordinator ensures that multiple SUAS are operated by vertical and horizontal distance and that each aircraft does not interfere with any other aircraft. The UAS coordinator is responsible for coordinating all UAS operations with manned aviation if these are operating on the same incident. The role of the UAS coordinator can be taken on by a qualified member of the ICS Air Operations Branch at the discretion of the IC or Air Operations Branch Director. Remote Piloting Command. The Remote Piloting Command is the person who has been found by the public safety entity to be properly qualified to exercise the privileges of remote pilot and has the final authority and responsibility for the operation and safety of the SUAS as determined by the authority having jurisdiction. Supporting roles are as follows. PMC, person manipulating the controls. This is a person who is either a trainee or otherwise qualified person who is in control of the SUAS. Visual observer, VO. This is a person who is assist the RPIC or the PMC to support seeing avoidance of other aircraft or objects aloft or on the ground. Other possible roles not necessarily defined by NFPA. Data observer. The data observer monitors or analyzes data captured by the SUAS either during or after a flight. Runner. Runners may be deployed to assist flight operations with supplying or otherwise supporting flight teams. For example, charging batteries and deploying them to flight teams. Compliance officers ensures that flights are performed safely and legally within the policies and procedures of the authority having jurisdiction, as well as local, state, and FAA laws. This is an example of an incident command facility. In this case, a well-equipped mobile command trailer. The UAS coordinator is monitoring and facilitating UAS operations through an electronic downlink from the aircraft. Incident command can be set up either in a mobile command unit or just the team huddled near the pilot. The roles and requirements do not change. NFPA 2400 Chapter 5 Professional Qualifications for SUAS Public Safety Personnel. Chapter 5 identifies the minimum job performance requirements, JPRs, for personnel supporting SUAS operations. These focus primarily on the roles of remote piloting command and visual observers. Other agency roles not currently defined by NFPA should meet agency-defined JPR standards. Chapter 5 of NFPA 2400 specifies the minimum job performance requirements for the roles of remote piloting command and for visual observers in support of public safety. Additionally, it provides guidance for agencies to ensure that individuals meet the qualification requirements to function within these roles. This chapter shall specify remote piloting command and visual observer positions for public safety entities. The intent of this chapter shall be to ensure that individuals serving as remote piloting command and visual observers in SUAS operations by public safety entities are qualified to do so. This chapter shall not address organization or management responsibility. Chapter 5 does not cover the management responsibility of these roles within the public safety organizational construct. It shall not be the intent of this chapter to restrict any jurisdiction from exceeding or combining these minimum requirements. JPRs for each level and position or task personnel shall be able to perform to carry out job duties. Public safety personnel who operate or support SUAS operations shall remain current with practices and applicable standards. Application. The application of this chapter is to specify which requirements within the standard shall apply to specific personnel who operate and support SUAS operations by public safety entities. The JPRs shall be accomplished in accordance with the requirements of the authority having jurisdiction, the AHJ, and all applicable NFPA and other standards developed by the Organization Standards, SDOs. Priority. It shall not be required that the JPRs be mastered in order in which they appear. The public safety entity shall establish instructional priority and training program content to prepare personnel to meet JPRs of this standard. The performance of each requirement of this chapter shall be evaluated by personnel approved by the authority having jurisdiction. JPRs for each level or position shall be completed in accordance with recognized practices and procedures or as defined by law or by the authority having jurisdiction. Public safety personnel who operate or support SUAS operations shall meet the requirement of this chapter for each make and model of small unmanned aircraft in operation by the organization. The public safety entity shall ensure that applicable equipment, personnel, protective equipment or PPE, force protection, and clothing are utilized for safe conduct operations. JPRs involving exposure to products of combustion shall be performed in appropriate PPE. Crew readiness. The availability and readiness of the remote piloting command and visual observer to deploy for SUAS operations given their knowledge and completion of pre-flight duties. Per PQU, Professional Qualifications for Unmanned Aircraft Systems. Data acquisition, the collection of information from SUAS for the purpose of fulfilling the mission objectives and goals in accordance with the mission plan. Again, professional qualifications for unmanned aircraft systems. Payload drop, release of any item or package from SUAS for the purpose of fulfilling the mission objectives and goals in accordance with the mission plan. Again, professional qualifications for unmanned aircraft systems. Positive aircraft control. Consistently maintaining appropriate control of the aircraft regardless of the phase of flight or potential distraction of other required tasks. Public safety personnel. Any individual involved with public safety that has a mission to protect life, property, or the environment, or any combination of these. Remote pilot in command. The person who has been found by the public safety entity to be the properly qualified to exercise the privileges of the remote pilot and has final authority and responsibility for the operation and safety of SUAS operations as determined by the authority having jurisdictions. Resources. The equipment, personnel, and facilities required for the SUAS operations provided by the Public Safety Department. Risk assessment. The evaluation of relative danger of SUAS operations when taking into consideration mission objectives and goals, SUAS professional qualifications of the RPIC and visual observer, operational readiness of the crew, weather conditions, environmental conditions, regulatory requirements, potential hazards, and operating conditions. UAS coordinator, sometimes known as the Air Boss, is a public safety person responsible for mission coordination and local deconfliction of multiple aircraft. The visual observer is a person who assists the remote piloting command and or the person manipulating the controls of the small unmanned aircraft system to see and avoid other air traffic or objects aloft or on the ground. This is per 14 CFR Part 107, 2016. Per the NFPA, the primary benefit of establishing national professional qualification standards is to provide both public and private sectors with a framework of the job requirements for emergency services personnel. Job performance requirements, JPRs, include the following three components. The task to be performed, which is a concise statement of what the person is required to do. The tools, equipment, or materials that must be performed for successful completion of the task. Evaluation, parameters, and performance outcome for both the performer and the evaluator. This portion of the JPR promotes consistency in the evaluation by reducing variables used to gauge performance. In addition to these three components, the JPR describes requisite knowledge, skills. The individual should have the requisite knowledge and skills prior to being able to perform the task, the foundation of task performance. Please take a moment to review this slide. In this slide, you see an example of a JPR that will be covered later. The text with the yellow shaded background is the task. The text with the green shaded background is the tool. And the text with the blue shaded background is the evaluation. At the bottom, item A are the requisite knowledge, and B are the requisite skills. Job performance requirements for remote pilot in command. The remote pilot in command shall meet all job performance requirements defined in section 5.3. The job performance requirements defined in section 5.3 shall apply to the following: normal conditions for SUAS operations, extreme or emergency conditions for SUA operations. Job performance requirements for visual observer. Visual observers shall meet the performance requirements defined in section 5.4. During flight, visual observers shall not perform other roles. The visual observer shall be trained prior to deployment in pre-flight, flight, and post-flight duties in accordance with public safety entities' operating procedures. Here are some suggested visual observer guidelines. Visual observers should keep their eyes on the prize at all times, or eyes on the aircraft. At launch, announce VO is Yankee. Yankee means yes, the visual observer has eyes on the aircraft. If the VO announces November, then the visual observer can no longer see the aircraft. Routinely, if appropriate, the visual observer should announce VO sky is Charlie, or the sky is clear. Announce an intrusion and location in the operational area. Civilian entering flight ground in area 3, or manned aircraft to the southwest. Announce obstructions in the immediate area of the aircraft. Obstruction at your 6 o'clock. If an emergency ensues, the VO should announce pilot emergency stop. Job performance requirements for the remote piloting command. Duties shall include performing pre-flight, flight, and post-flight functions for SUA operations. Pre-flight, the pre-flight JPR is shown on the next slide. Job performance requirements for remote piloting command. Plan SUAS operations given mission objectives and goals, resources, environmental conditions, and scenarios so that the mission plan is completed that aligns with the mission objectives and goals, identifies the resources required, assesses the risks associated with the mission, and identifies the operational tasks necessary to complete the mission. The requisite knowledge of airspace requirements, weather conditions, crew readiness, resource capabilities, ICS, risk assessment, and regulatory requirements. Requisite skills, the ability to produce and communicate a mission plan. Mission planning. 3 primary components. Either one fails the test, the mission should be canceled. A clearly defined mission plan to ensure that mission objectives can be met. Airspace authorization, either in the form of LANC requests, certificate of authorizations, or certificate of waivers, or all of the above. Favorable VFR weather conditions, adequate ceiling, calm winds. These are examples of a mission plan, an airspace check, and a weather check prior to a mission. Job performance requirements for remote piloting command. Prepare the SUAS operation given mission plan and resources so the SUAS is operated by confirming a state of readiness that demonstrates possession, configuration, operational functions are checked and verified as operational. Requisite knowledge of procedures and information needed to identify the operational functionality of an SUAS. Requisite skill, the ability to identify, assemble, configure, and verify the operational function of SUAS. The next section covers the flight job performance requirements for the remote piloting command. Perform takeoff under the regulatory requirements as determined by the authority having jurisdiction given a specific SUAS and confirmed state of readiness so that the SUAS takes off after having completed system checks and flight as initiated and maintained in a manner compliant with regulatory requirements. Requisite knowledge of the aircraft systems, payload, and changes in environmental conditions, weather, and regulatory requirements related to the use and operation of an SUAS. Requisite skill, the ability to operate the specific SUAS and maintain control in a safe manner during this phase of flight. Flight job performance requirements for remote piloting command. Maintain visual line of sight of a given SUAS in flight along a designated flight path under the regulatory requirements as determined by the authority having jurisdictions so that the SUAS is maneuvering in a manner that avoids obstacles and reaches targeted locations and altitudes without losing line of sight of the SUAS in accordance with the approved operational flight plan. Requisite knowledge of the regulatory requirements, capabilities, and operational controls of a specific UAS. Requisite skills, the ability to operate the specific SUAS and maintain control in a safe manner during this phase of flight. Flight job performance requirements for the remote pilot in command. Perform aerial maneuvers given an SUAS in flight with designated airspace under the regulatory requirements as determined by the authority having jurisdiction, so the operator demonstrates positive aircraft control in accordance with the approved operational flight plan. Requisite knowledge of the regulatory requirements, capabilities, and operational controls of the specific SUAS. Requisite skills, the ability to operate the specific SUAS, activate different SUAS functions, and maintain control in a safe manner during this phase of flight. Flight job performance requirements for the remote pilot in command. Perform payload functionality given an SUAS in flight within a designated airspace under the regulatory requirements as determined by the authority having jurisdiction, so that the SUAS is maneuvered in a manner that avoids obstacles and demonstrates payload drop, payload application, or data acquisition at a targeted locations in accordance with the mission's plans. Requisites knowledge of the mission plan objectives, regulatory requirements, capabilities, operational payload functions, and operational controls of the specific SUAS. Requisite skills, the ability to operate the specific SUAS, activate different payload functions, and maintain control in a safe manner during this phase of flight. Flight job performance requirements for remote pilot in command. Perform pre-landing procedures given an SUAS in flight within a designated airspace under the regulatory requirements as determined by the authority having jurisdiction, so that the SUAS is maneuvered in a manner that avoids obstacles while reaching a clear landing area, establishes a configuration for landing, and confirms a decent path free of obstructions. Requisite knowledge of aircraft systems, payload, and the effects of changes in environmental conditions, weather, and airspace requirements for the specific SUAS. Requisite skills, the ability to operate the specific SUAS, maintain control in a safe manner during this phase of flight. Flight job performance requirements for the remote pilot in command. Perform landing given an SUAS in flight with a designated airspace under the regulatory requirements as determined by the authority having jurisdiction, and completed pre-landing procedures so that the SUAS is maneuvered in a manner that avoids obstacles and is able to touch down at a clear landing area and ceases operational functions without damage to the SUAS. Requisite knowledge of small unmanned aircraft systems, payload, and the effect of changes in environmental conditions, weather, and airspace requirements for the specific SUAS. Requisite skills, the ability to operate the specific SUAS, maintain control in a safe manner during this phase of flight. Post-flight job performance requirements for the remote pilot in command. Complete post-flight procedures given an SUAS that has performed a successful landing, so that the SUAS is visually inspected for damage, configuring for transport and storage, confirm ready for service through immediate maintenance, or out of service for scheduled maintenance. Requisite knowledge: knowledge of small unmanned aircraft systems, payload, transport mechanisms, and storage procedures for the specific SUAS. Requisite skills: the ability to complete logbooks, forms, records, and any digital media programs for information from the SUAS operations. Post-flight job performance requirements for the remote pilot in command. Conduct a mission debrief giving a mission plan and ended SUAS operations so that the operational tasks necessary to complete the mission are identified as complete, incomplete, or deviated from the designated mission plan for specific reason. Requisite knowledge: knowledge of the mission plan, elements, contents, and potential impact of changes in environmental conditions, weather, and regulatory requirements on the specific SUAS. Requisite skills: the ability to communicate and present information obtained from SUAS operations. Job performance requirements for the remote pilot in command. Flight duties shall include performing pre-flight and in-flight functions for SUAS operations. Pre-flight: job performance requirements for the remote pilot in command and visual observer. Evaluate operational role given a mission plan, remote pilot in command, and SUAS operation so that the operational tasks necessary to support the mission are identified, listed, and communicated to the RPIC, the remote pilot in command. Requisite knowledge: knowledge of airspace requirements, weather conditions, and regulatory requirements. Requisite skills: the ability to review, understand, and support a mission plan. Flight: maintain visual line of sight of a given SUAS given and remote pilot in command and an SUAS in flight along a designated flight path under the regulatory requirements as determined by the authority having jurisdiction, so that obstacles are identified and communicated to the remote pilot in command prior to potential collision and in a time that allows for corrective action. Knowledge of regulatory requirements and operational and flight capabilities of the specific SUAS. Requisite skills: the ability to communicate verbally to the remote pilot in command. In this slide, let's review a pre-flight piloted skills checklist. Knowledge of the mission plan and objectives. Identify the operational tasks, equipment, and personnel to complete the mission. Set up incident command and control. Remote pilot in command, crew briefings, and checklist processes. Identify airspace requirements and authorization. Perform weather assessment. Identify crew readiness and capabilities. Perform risk assessment and risk mitigations. Prepare aircraft systems to support the mission. Prepare payload and other payload systems to support the mission. In this slide, let's review an in-flight pilotage skills checklist. Ensure knowledge of aircraft systems and limitations. Perform takeoff and other system checks. Monitor environmental conditions during flight. Maintain visual line of sight along the designated flight path and maneuver the aircraft to avoid obstacles and reach targeted locations. Operate specific SUAS and main control in a safe manner. This includes maintain position, fly straight and level, move and rotate, avoid obstacles or other hazards, land accurately. In this slide, we continue to review the in-flight piloted skills checklist. Perform payload functions to support the mission. Includes payload drop and data acquisition. This includes the following: point and zoom cameras, identify objects, inspect objects, map wide areas, drop accurately, complete the mission objectives, and perform safe pre-landing procedures that avoid obstacles or hazards. Complete a safe landing at the designated LZ landing zone in a manner that ceases flight operations without damage to the aircraft. In this slide, let's review a post-flight piloted skills checklist. Secure aircraft controls so the aircraft can be approached safely. Conduct a mission debrief given a mission plan and ended SUAS operation. Complete all logbook entries, forms, digital programs, or other records required by the authority having jurisdiction. Secure and protect data acquired by the SUAS for evidentiary purposes as required by the authority having jurisdiction. Process the ability to or hand off digital data for post-mission processing. Have the ability to communicate and present information obtained to and from the SUAS operation. Communication is a key word in all phases of the operation. In this slide, let's review a flight crew's skills checklist. Basic knowledge of regulatory requirements. Assist the remote piloting command in identifying obstacles and possible intrusions to the designated operations area. Utilize see and avoid techniques to safely conduct, fulfill the mission objectives, and communicate with the remote pilot in command. Coordinate SUAS operations and communicate instructions to the flight crew. Understand and utilize technologies associated with SUAS operations. SUAS data observers are not identified by the NFPA. Secure aircraft and flight ground equipment in a readiness state for the next mission. Secure digital media as evidence that NFPA 2400 Appendix. Uses of SUAS in firefighting environments can include, but are not limited to, the following: assessing thermal conditions, hazard identification, personnel tracking, victim location, atmospheric monitoring if equipped, temporary illumination, assess structural status, identification of urban interference, identification of fuel types, identification of shelter locations, identification of evacuation and escape routes, identification of fuel load.
The first step of hazmat response has classically been walking into the unknown. Now drones face the unknown for us. Hazmat response is not fast, It takes much longer than many other forms of emergency response because you don't always know what you're dealing with, and it's dangerous. We deal with biological threats, chemical threats, and nuclear threats. The problem is we don't always know which one it is. So we send a guy in there first with meters and hope he's all right, because no single suit can protect you from everything. These are fathers and sons, mothers and daughters. Equipment is disposable. People are not. Sometimes we forget the ones going in to save lives are people too. And we have to protect them.
We have a very progressive department here at Southern Manatee, and that's allowed us to develop new tech. We started talking about using drones back in 2015. We looked at other options, but platforms like DJI's Inspire and M210 series have more capabilities and are much more cost effective. Before we get too close to an incident, we kind of want to make sure that the drone won't cause a spark that would ignite something flammable. So we want to test them beforehand. So far, every test that we've done with DJI's aircraft have had positive results. None of them have had any flammability issues. We really wanted to use the drones for more than just your basic eye in the sky. We wanted to use the drone in a way that could take some of the burden off our tech, such as recon, hazard ID, metering, and remote sensing. We worked with a company to design a bracket that could hold a hazmat meter for us while we're flying the M210. And just simply by using the onboard camera, we can turn it around and look right at the meter and get real-time data. One of the great things about it is we can carry our handheld meters down there without having to actually carry the meter down there ourselves. With the new payload SDK, we're hoping to be able to integrate some of these sensors right into the aircraft itself. In the future, we're hoping to be able to deliver payloads into some of these hot zones, carry things like tools, supplies, or whatnot. Not only does drone technology keep us safer, but by dramatically reducing our response time, it keeps the public safer as well.
This is changing the way things have been done for the last 100 years. And it's changing it for the better.
Uses of SUAS in a search and rescue environment can include, but are not limited to, the following: missing person search, confirm victim locations, delivery of supplies, monitoring conditions of victims, a visual beacon, temporary illumination, radio direction finding, locate, assess routes for ground teams, 3D imaging and search area or incident site, assessing structural integrity. In the United States, the applicable patient privacy regulations are referred to as the Health Insurance Portability and Accountability Act, HIPAA, of 1996. It provides data privacy and security provisions for safeguarding medical information. This will change based on the country you are operating from and what applicable patient privacy regulations are. Uses of SUAS in hazardous materials response can include, but are not limited to, the following: site survey, material identification, container identification and condition, monitoring product migration, delivery of supplies, identify ingress and egress routes, temporary illumination, personnel accountability, monitoring decontamination operations, atmospheric monitoring if equipped. This concludes our review of NFPA 2400, Chapter 4 and Chapter 5. In the next segment, we will review the U.S. Department of Commerce, National Institute of Standards and Technologies, unmanned aviation training and testing processes. NIST testing lanes and processes. Testing scenarios for vertical takeoff and landing systems equipped with onboard cameras and remote pilot displays.
Roswell Flight Test Crew, here in Atlanta, Georgia for Exponential 2021. And I'm here at the Mercedes-Benz Stadium with Adam Jacob. How you doing, Adam?
I'm doing well. Pleasure.
Good, good. Now you're with the National Institutes of Standards and Technology, but we're at a drone conference. What's going on here?
Yeah, so NIST has been leading an international effort to develop standard test methods for emergency responders in general. And that's ground robots, that's underwater systems, and it's unmanned aircraft systems, drones.
All right, now in the background here, we've got all these buckets set up on the soccer field here. What's with the buckets?
So, well, this is a drone specific set of tests, and the buckets are a way to get everyone to be developing their own standards. So these are standard test methods that are replicated all over the world because they're as simple as buying some buckets, printing out some stickers inside, and looking for all the stickers that you placed in your environment.
Got it. So when I go out here and complete this card, do I get like a NIST certification that says I'm a great drone pilot, or how does that work?
So NIST does not certify, NIST does not train. What we do is lead the standards development effort. And then these standards go through ASTM International, Committee on Homeland Security. There is a standards process that we feed, and I have to chair that committee. So these are ASTM standards that people can then replicate and set thresholds as they see fit. So everyone can set their own threshold. New York might have a different threshold than Ottumwa, Iowa, but those thresholds can then lead toward credentials provided by other organizations.
Got it. Now, do the standards change over time, or can you compare one person to the next, or how does that work?
So the standards, well, once they're standardized, standards take some care of feeding over time. They can be edited. You know, every 5 years you need to open them up and make sure they're still right. We've been validating these tests in particular for the last couple of years, and so they're pretty fully baked. They're going through the standards process now. The power of these standard test methods is that you can compare yourself, your score today, to your score 2 weeks ago, to your score 2 weeks hence, right? So the standard test didn't change, maybe your proficiency changed. And to even measure your proficiency, it's not a one-time thing, it's an ongoing thing. So the average of your last 5 flight tests might be a really good indication of your actual proficiency. That number is completely comparable to anyone else who's using the exact same test with the exact same aircraft. Comparable across countries, across time. It doesn't matter where or when you conduct your evaluation. You can then leverage the data coming out of all of those other flight tests.
Got it. Now, is it? We've got a bunch of lanes set up here. Is everybody taking the same test here? Is that how that works?
So every lane that you see here right behind us are the open test lane. This is the basic course. This is the accompaniment to the Part 107 knowledge exam. So this is the skills level course of it. So there's 5 different flight paths in that test alone. There's also a lane of obstructed tests along the wall. Those are harder, closer proximity to objects of interest, to walls, to windows, to vehicles, to packages. And that requires you to fly much closer to the world than you're typically comfortable. But they, because of the buckets, allow pilots to feel safe when they're there, because the buckets, 2 buckets verging to a point, makes you know that you're in a safe location, and it allows you to look around, understand your interface, see what distortions are in your field of view, and start controlling for contrast and zoom and working your system more rigorously.
Got it. Now, of course, we've had Part 107 for a number of years now. Why do we need something like this?
Well, the 107 was an essential first step. It's a knowledge exam, though. It makes sure that people understand where their nearest airport is, a little bit about the national airspace, some weather, some aerodynamics. This is important because this is the practical skills test. So you might be very knowledgeable about the national airspace, but you might be a hazard at the control of a drone. And this test either informs you that you're a hazard or shows you where your weaknesses are until you can rise above a certain threshold that says safe, effective, maybe even great at it, and deployable for an emergency response organization that needs to go into really, really complicated, difficult environments.
And then if I am that emergency response organization and I sort of want to bring the rigor and the strength of this testing process, how do I go about that? What's my point of contact? Where do I start?
So, well, we've made a lot of contact through events like this. You know, it's just a general call to the local police, Atlanta Fires, put out the word, and we have more than 100 people here. So everyone's kind of craving this notion of standard tests because everyone wants to evaluate themselves and start comparing notes. So we filled a void that was absolutely necessary. Generally speaking, across the nation, we are helping get these test methods out there through our website because we've been validating that they scale across the country. You know, we go to other countries too. Canada's big in using them, Japan, Germany, but across the United States, there are whole states that have adopted these tests already, helping to validate them along the way. Texas Department of Public Safety, Colorado Department of Public Safety, statewide implementations that show that these standard tests can scale. That's the goal.
All right. Well, Adam, thank you so much. Very informative and very interesting. Appreciate your time.
Pleasure.
And from Exponential 2021 in Hotlanta, Georgia, this is the Roswell Flight Test Crew signing off. Thanks again, Adam.
Yeah, you're welcome.
NIST utilization. Appliance and courses can be used as a standard standalone testing system or can be customized for multiple agency-specific training scenarios, also known as embedded scenario scoring. NIST testing and training processes can be reviewed online. Simply search for Aerial Systems NIST. From here you can download and review NIST processes and tools. This is recommended reading if your agency is going to adopt these processes. Within are different applications for these tools and material downloads. For example, target placards or stickers for the course OmniBucket stands. There are 8 NIST training and testing sections. Basic maneuvering, man 1 through 5, designed to train, test piloted skills of individuals and establish their credentials as a pilot. Aircraft payload functionality, pay 1 through 5, designed to test performance of aircraft platforms as a units. Number 3, point and zoom cameras, sensing 1 through 5. Number 4, obstructed wall, 90, 45 degrees. Man pay, 6 and 7. Obstructed lane, ground, post, avoid. Man pay, 8, 9, and 10. Number 6, embedded scoring scenarios. Vehicle inspection, box truck inspection, fuel truck inspection, wide area search. These are all custom scenarios. Deliver, other tests. Endurance, energy, other tests. Sections 3 4, 5, 6, 7, and 8 are not covered in this introductory class. Evaluation criteria is broken out into two separate testing scenarios. Evaluation measures for remote pilot proficiencies. These include basic skills tests, the ability to safely and legally operate in the national airspace, NAS, not to be a hazard to other SUS or manned aircraft, track times, scores, and performance improvements. The second group is evaluation measures for unmanned aircraft system capabilities, flight times with payload, safety and compliance, landing accuracy, and position stability. The pilot operates within line of sight of the lane and the aircraft, or with their back turned to the lane to represent flying beyond visual line of sight, with a visual observer to ensure safety. The aircraft performs a series of basic flight maneuvers, designated positions, and orientations along a lane centerline with a variable spacing of S between omni bucket stands. The aircraft simultaneously aligns with two buckets in each position, orientation, and altitude. For each alignment, it pauses long enough to capture a single no-zoom image showing the inscribed green ring. An additional full zoom image can also be captured to identify the visual acuity target inside. Conduct tests in two ways. Basic maneuvering, MAN, for testing, training, pilotage skills. Align with buckets and land accurately. Align with each bucket long enough to capture a single alignment image with no zoom showing the ring inside the bucket. Score 5 points for a continuous ring or 1 point for a partial ring. Similar scoring for accurate or partial landings. Payload functionality, PAY, for testing aircraft capabilities. Align with buckets and identify acuity targets. Align with each bucket long enough to capture a single alignment image, no zoom of each bucket, and a single acuity image. Max zoom of each target. Score 1 point for each correct identification of the 5 increasingly small concentric ring gap directions. Note, there are 20 possible target alignments, up to 5 points each per target. The maximum score equals 100 points per lane. Summary of test methods. These test methods are performed by a remote pilot in direct line of sight of the testing lane. An optional technique is with the pilot's back turned to the course and directed by a visual observer. This is a beyond visual line of sight test scenario. The pilot performs the series of maneuvers around the apparatuses in the testing lane. Align aircraft camera with one or more buckets to identify recessed targets inside. Successful alignment is achieved when no corrections are necessary to verify an unobstructed view of the target at the bottom of each bucket. Summary of testing methods continued. Additional targets inside evaluate camera pointing and zooming capabilities including visual, color, and thermal acuity, hazardous material labels, or other objects of interest. Environmental conditions can be controlled indoors for lighting and wind. Outdoor conditions should be chosen purposefully so not to affect the results. Faults include extreme deviations from the intended flight path or contact with the apparatus, ground, or safety enclosure. Time-limited testing. This is not intended to be a competition. The emphasis is on performing each task successfully until the evaluation is complete. Use a count-up timer to capture statistically significant data for comparisons. Flights 10 minutes or less ensures the overall training or evaluation is completed in a deterministic amount of time across multiple test scenarios. Time limits should be ample for an expert pilot. Pilots are presumably exhibiting the 100th percentile of proficiency on that system, so the time limits can vary for different systems with different capabilities if necessary. If a perfect score is completed within the time limit, record the elapsed time as a point of comparison. The average elapsed times of a series of perfect trials can be used to identify the more efficient systems or pilot techniques. If using a time as a pass-fail threshold, it should be long enough that a passing pilot can perform at least 10 tasks with a perfect score, which is half a trial. Allowing enough time to complete the entire trial provides more confidence in the resulting system capability or pilot proficiency. Test trials shall produce enough successful repetitions to measure the system capability or remote pilot proficiency with reliability and confidence. There are 3 performance metrics to consider in order. Number 1, completeness. This is the primary metric. If you can't finish a trial without faults, just keep track of how far into the trial sequence you get until you are reliably finished the trials. Completion of a statistically significant set of repetitions, 20 or more, is essential to measure the reliability of the task being performed. So a complete trial with 20 task repetitions should be performed to score the trial. Number 2, score, secondary. For complete trials with 20 task repetitions, the score is the total of points earned. To determine your proficiency, track your scores over time and calculate the average of the most recent 5 trials. That running average can be compared to others using similar systems in similar test lanes. Average score or points equals total points in the last 5 trials divided by 5. Efficiency, tertiary. If 2 systems or pilots are consistently completing trials and their average scores are perfect, then the efficiency can help identify the most effective system or pilot techniques. The elapsed times of the trials in second needs to be tracked as well to calculate the average elapsed time of the last 5 trials. Average time equal total seconds of the last 5 trials divided by 5. The efficiency or average rate of successful tasks completion can then be calculated. Efficiency or points equals the average score divided by the average time. There are 2 types of NIST apparatus: Omni bucket stands, OBS, tower bucket stands. Their utilization is wholly dependent on the testing method being utilized. Typically, 4 Omni bucket stands or stations are used for standard version 2020 B2. This results in 20 targets, 5 points each for a total of 100 points to be used when scoring. Testing Lane Overview, version 2020 B5. Pilot flight lane and lane markers maintained safely. Center line is along a measuring tape or a line by other means. Spacing S equals 10 feet, 20 feet, 30 feet, or other. Overall length 10S equals 100 feet, 200 feet, 300 feet, or other. Shown is the NIST linear test lane for man 1 through 5 and pay 1 through 5. The linear test lane contains 4 Omni bucket stations. Testing Lane Overview, version 2020 B5. Spacing is reflected in 3 dimensions. The value of S depends on the lane configuration. 1. Distance between each Omni bucket station. 2. Define altitudes from AGL to observation points. 3. Orbit radius from the center of the Omni bucket station outward. Let's discuss Omni bucket station azimuth. For example, shown is Omni bucket station 1. Numbers change at each station. For example, station 1, 2, 3, and 4, or other if a custom course is set up. Notice the bucket azimuth for A, B, C, and D. Azimuth A faces the pilot. In the fire service, this is known as the address side of an incident scene. Rotating in a clockwise direction from A, or as noted as CW on diagrams, or to the left, is azimuth B. Rotating further is azimuth C, continuing the rotation to azimuth D, then returning once again to the A side of the station. Bucket stations and bucket locations are indexed for pilot instruction and scoring purposes. For example, Station 1, the center bucket, is the station bucket. Buckets 1A, 1B, 1C, and 1D are in direct correlation to the station azimuth. Shown is the UAS Incident Response Grid. This grid is used to locate areas of concern, personnel, equipment, and the aircraft at an incident scene. Notice the direct correlation to the NIST Omni bucket azimuths. There are 2 types of targets: letter, placard, or object shown on the left. Acuity targets are shown on the right. A fully aligned target is represented on the left side of this illustration. A full alignment is scored as 5 points. A partially aligned target is represented on the right side of this illustration. A partial alignment is scored as 1 point. When the pilot stops maneuvering the aircraft, that is the moment when the judge scores the target. Landing accurately is defined as 3/4 of the aircraft within the rings of the landing pad. This is also worth 5 points. Acuity means a keenness of perception. Acuity placards or stickers inside each bucket have a color inscribed ring to guide alignment and visual acuity with increasingly small concentric C's with gaps shown in a red circle to identify the correct 1 of 8 random orientations. The typical color is green, although blue, yellow, and orange are available as well, per NIST 2020 BS. Score 1 point for each correct identification of the 5 increasingly small concentric C gap directions. The radial shown is how the pilot should communicate the rings acquired. For example, ring 1 left, ring 2 bottom, ring 3 right, and so forth and so on. This slide shows an actual full alignment. This slide shows an actual partial alignment. This slide also shows an actual partial alignment. The bucket target should appear to be at least 1/10 of the overall control station display width or larger. In the setup of the linear test lanes, S represents spacing between omni stations, the altitude above them, and the radius away from them. In the test lane shown from left to right, the pilot the primary LZ, and stations 1, 2, and 3 are at the S value apart, or at an equal distance. Station 3 and 4 have a distance of 5S, or 5 times the distance of S. In addition, there is an alternate LZ with a value of S from station 4. So a test lane with a S value of 10 feet should be 100 feet in length. An appropriate lane spacing is when 2S hover allows reading at least the outer concentric C target 2 stands away. This illustration shows the correlation of S as a distance, S as an altitude, and S as a radius. There are 5 standard test lanes designed for maneuvering and payload testing, known as Man-Pay 1 through 5. These are as follows: position lane, Man-Pay 1, traverse lane, Man-Pay 2, orbit lane, Man-Pay 3, spiral lane, Man-Pay 4, recon lane, Man-Pay 5. In addition to these standard test lanes, variants can be developed to support your agency's individual requirements. This is a copy of page 7 of the NIST manual. It provides a quick glance at all 5 test lanes. We will go over each one later in this presentation. This is an illustration of the position test lane, or Man-Pay 1. Purpose: this test lane evaluates positive aircraft control using basic flight maneuvers between designated hover positions, orientations, and altitudes. It can be used to evaluate system capabilities as a repeatable training task or as an evaluation of remote pilot proficiency. This is another view of Man-Pay 1, which is shown in a plan view and is color-coded for the direction of travel of the aircraft. This is an illustration of the traverse lane, or Man-Pay 2. Purpose: this test lane method evaluates sideways maneuvers along a designated flight path parallel to a line around objects at a designated standoff distance and altitude. It can be used to evaluate system capabilities as a repeatable training task or as an evaluation of remote pilot proficiencies. This is an alternate plan view of the diverse Man-Pay 2. Notice the counterclockwise and clockwise paths around the course. Perform each as a separate run, landing in between. Shown is an alternate to Man-Pay 2 It includes all 4 omni-bucket stations instead of just 3. Same process, a counterclockwise rotation, land with a clockwise rotation, and land. This is an illustration of the orbit test lane, or MANPAY 3. Purpose. This test method evaluates orbiting maneuvers to identify objects of interest from a designated radius and altitude. It can be used to evaluate system capabilities as a repeatable training task or as an evaluation of remote pilot proficiencies. Here's another view of MANPAY 3. Notice the clockwise orbit of Station 3 at the S altitude and S radius. Also notice the counterclockwise orbit at a 2S altitude and a 2S radius over Station 3. As the aircraft passes over Station 1, the station identification placard should be in view when looked down vertically. This is an illustration of the spiral test lane, or MANPAY 4. Purpose. This test lane method evaluates free flight maneuvers to inspect objects of interest from any radius and altitude. It can be used to evaluate system capabilities as a repeatable training task or as an evaluation of remote pilot proficiency. Please note, CW indicates a clockwise rotation. CCW indicates a counterclockwise rotation. This is an alternate view of MANPAY 4. Notice the clockwise and counterclockwise rotation over each station. When the course is complete, free fly to the LZ. This is an illustration of the recon test lane, or MANPAY 5. Purpose. This test method evaluates straight and level acceleration and decelerations in and out of stable hovers over objects of interest at designated altitudes. It can be used to evaluate system capabilities as a repeatable training task or as an evaluation of remote pilot proficiencies. Again, note, CW indicates a clockwise rotation and CCW indicates a counterclockwise rotation. This is an alternate view of MANPAY 5. Notice the counterclockwise and clockwise rotations at either end of the course. Station alignments are along the center line of the course, requiring bucket azimuths A and C for each station. Available on the NIST website and also available for download and publication is the Pocket Guide for Aerial Drones, Open Area, Test, and Scenarios. This is a useful document for implementation of NIST processes. Most importantly, it contains the standard NIST score sheets and scripts for each of the 5 test lanes which we have reviewed. This is an example of a NIST open lane script score sheet. Shown is the position man-pay 1 test lane score sheet. Shown is a customized digital scoring system for NIST. You can purchase and use such a system as this or develop your own on any platform you desire. The system shown is available through Hunter Remote Aviation at a minimal cost. Here is a list of other test methodologies defined by NIST. Scenarios with embedded scoring. A wide area search. 4 stands, 20 targets, 100 points. Rubble search. 4 stands, 20 targets, 100 points. Vehicle search. 1 stand, 20 targets, 100 points. Truck inspection. 4 stands, 20 targets, 100 points. Interior structure inspection. 4 stands, 20 targets, 100 points. Exterior structure inspection. 4 stands, 20 targets, 100 points. This slide shows NIST trial settings for varied credentials. Credentials for standard operations, daylight or line of sight operations, beyond visual line of sight operation, and night ops. Refer to the NIST manual for more information. Thank you. This concludes this training program. For more information, contact Blue Ridge Mountain Drones or Hunter Remote Aviation LLC. Thank you.